review on the board to make sure everyone's sort of on the same page. I'm not going to go into the amount of detail, like with all of the photo systems, all of that detail here. I just want to make sure you guys have kind of an idea of the main points that we talked about and some of the take homes on Monday with those, the first half of photosynthesis, basically. All right. So I will say, hang in there. We are almost done with biochemistry, which is excellent. Very little chemistry after this. So this is the last little bit of information that will be on the next exam, which is Monday, right? So we'll do a review on Friday. I should get through the rest of this today. And then there will be a teeny tiny bit of chemistry when we talk about DNA replication, but thank God for the most part, we're moving on from biochemistry. You guys just hang in there one more day. Okay, so I'm just gonna sort of list the steps and I'll ask you guys if you can remember any of these pieces. Feel free to look at your notes. So I think you guys on Zoom should be able to see me okay. Right in the right spot here. Okay. So first, we were talking about, remember there's the light dependent and the light independent reactions, right? So this is the first half of photosynthesis are the light dependent reactions. So this is where the light is absorbed. The point of absorbing the light is so that energy can go on to the light independent reactions. So that's the whole part. So it's the whole reason for this first kind of half of photosynthesis. So what we get first, light hits the leaf. That has to happen, right? So that's where we're getting the initial energy. That's why the sun is kind of the ultimate source of all energy on Earth. And so light's hitting the leaf. That's pretty easy to understand. Do you guys remember the name of the molecule that absorbs that light? What's that? It starts with a C. Yeah, chlorophyll. So chlorophyll absorbs that light. So the light comes into the leaf, specifically within the leaf, chlorophyll is absorbing it. That is a specific molecule, and the chlorophyll, when it absorbs that energy, its electrons get all excited. So it excites the electrons.
Is it giving it a positive or negative?
It's not giving it a charge. The electrons are negatively charged, so they're just getting all excited. And then the next step is they'll get passed along, essentially. Yeah, so no charge change necessarily. Electron looks excited. Whatever. They get excited. So then I'm skipping over some details here. Water has to be split, all this stuff. But again, I'm just kind of trying to give you the overview of what we're doing, kind of where the energy, because we're moving into the Calvin cycle. So I want to show you kind of where that energy is coming from. So these electrons, when they get excited, they get kind of passed along to an electron transport chain. So ETC. We had an ETC in respiration, right, where the electrons get passed along. And that provides power for something. Do you guys remember what the electron transport chain? It powers the same basic process in both respiration and photosynthesis. It's pumping something. Close. It's an ion. Yeah, so it's pumping the hydrogen ions. Yeah. So the electron transport chain powers pumping of hydrogen ions across the membrane. It's a different membrane in respiration versus photosynthesis, but we're trying to get hydrogen ions onto one side of the membrane. So we're building up this concentration of hydrogen ions. So that's what the electrons are doing. By then going down the electron transport chain, that's going to power this pumping of hydrogen ions. Okay. So the electrons, after they go down this electron transport chain, they end up on an electron shuttle. Do you guys remember what the electron shuttle is for photosynthesis? This is kind of, I mean, not tough, but it's similar. It's very similar to respiration. We just have one extra letter in the molecule. Starts with an N-A. Yeah, NADPH or NADP plus, however you want to say it. So when the electrons are on it, it becomes NADPH. So I'm just going to call it that.
Oh, this is the one where it loses it and it gains it?
Yeah, exactly. So electrons end up on what we call NADPH. That's our electron shuttle. So they're getting taken over to the Calvin cycle. So that's what we're going to talk about today. So electrons are going to the Calvin cycle after they've powered this pumping. So then, okay, we have all these hydrogen ions on one side of a membrane. So what are those hydrogen ions going to do? They're on one side of the membrane. They're going to flow back to the other side of the membrane. And what does that produce? Something else that's going to help power the Calvin cycle. They're creating a gradient. Yep. So we're creating an H plus gradient. So there's a lot of hydrogen ions on one side. They're going to flow back through ATP synthase to make ATP. Yeah. Yep. So these hydrogen ions flow back through ATP synthase. And that's that crazy protein that's like a motor. So it rotates as the hydrogen ions come through it. And that makes ATP, which is also going to be used for the Calvin cycle. Those are the main pieces of what we talked about. There's some extra details in there that you need to know that we went over. But we get to the point where electrons going to the Calvin cycle, ATP going to the Calvin cycle. So all of this is just powering the Calvin cycle, which is the last half of photosynthesis.
I have a question.
Yep.
Okay, so the NADP or NADH, all that stuff, it really confused me. So like, is there like, what does it stand for?
Don't worry about it. I would tell you, but it's a really long molecular name. It's just, you can think of it as a little, like I said, an electron shuttle. So if you have, here, let me erase some of this. Do you guys have all of this? We good? Okay. Yeah, NADH and NADPH are some of the more confusing parts. But if you break it down, all they are, the point of them is to move electrons from one point to another. So if you have, we're talking about photosynthesis, so I'll stick with the P. So you have NADP plus, and then if you add an electron to that, you get NADH. So think of that H, NADPH, sorry. So think of that electron as the hydrogen.
Okay, so when we see the P on the, not the P, the P on the NAD, that's like for photosynthesis.
Oh yeah, yeah. So yes, NADP is photosynthesis. Anytime you see that P, think photosynthesis. Respiration is just NAD plus.
And with the H, that means an electron has been added.
Exactly, yeah. So if you have the H on either of these, that means it's carrying an electron.
It's already picked it up.
Mm-hmm.
Okay, so where does the electron go?
We're going to get to that with the NADPH. So in respiration, NADH took the electrons over to the electron transport chain at the very end of respiration. Because then it released the electrons and they flowed down that chain.
Okay.
And then we'll talk about where the electrons are going in just a minute in photosynthesis, but those are excellent questions. I'm glad you brought that up.
Thanks.
Good. Any other questions about this? Okay, good. All right, moving into the Calvin cycle. Okay, now I cut down the end of this a little bit. So if you have an older version, oops, I should turn the projector on. If you have, I think I uploaded the newer version yesterday, but it doesn't change until we get into kind of the last few slides. I just simplified things a little bit and cut out some details. So if you downloaded the PowerPoint before yesterday, I think it was, maybe Monday, I don't remember when I did it. Yeah, the light independent reactions. So that PowerPoint, sorry, yes, the light independent reactions. If you downloaded it before yesterday, you may have some of the older, more detailed slides at the end. So just FYI, but I put the new version up, I think yesterday, I'm pretty sure it was yesterday. So check that out if your slides don't match what I'm showing up here. Okay. Yeah, last half of photosynthesis. Is the light independent reactions or the Calvin cycle. So same thing. The cycle is the only part of this basically. So we just have one cycle to talk about. Then we're done with all of this photosynthesis. Well, the biochemical part of it. Okay. So now this was the last slide I showed at the end of the lecture on Monday. So we were talking about what's happening here, the light dependent reactions, all of that's happening in the membrane of the thylakoid. As a reminder, the thylakoids are those little coin-shaped stacks within the chloroplast. So in the membrane of the thylakoid is where you have these photosystems and light actually being absorbed. Here we made our ATP. Here we have our electrons on NADPH. All of those are going to the Calvin cycle. So we're going over here to the Calvin cycle. Oh, make sure you guys can see that. Okay. That's happening in the stroma of the chloroplast. The stroma is just the liquidy stuff that fills up most of the chloroplast outside the thylakoid.
We need to know that.
Yeah, the stroma of the chloroplast. So the location of all these things is really important. So I don't just mention it, for fun. I will probably ask you about the different locations of what happens in respiration and photosynthesis. Not all of them. I don't have enough room on the test to ask you about all of them, but you want to know where all of these processes happen. Okay, so that's where we're going. Calvin cycle outside the thylakoid, just in the liquidy stroma. But we're still in the chloroplast. All of this happens in the chloroplast. Okay, so we have 3 phases of the Calvin cycle. It's just a cycle. This isn't showing up very well on here, sorry, but there's a cycle that's happening. So it's kind of broken down into the beginning, the middle, and the end. So what the Calvin cycle is doing, if we step back for a second before getting into the details of it, it's using that energy that was produced by the light dependent reactions. So the plant absorbed all this energy, made ATP. So it's going to use that in order to make glucose. So now we're finally going to get to the point where glucose is made. That's our most important product, right? Well, I guess oxygen is also really important, but the point of photosynthesis is to make glucose. The first step is called carbon fixation. And we haven't talked at all about carbon in this whole cycle, and carbon's pretty critical to glucose, right? There's 6 carbons in each molecule of glucose, so we got to start bringing that in to actually be able to make glucose. So that's the carbon fixation part, taking CO2 and making glucose out of it, an organic molecule. Then you have 2 stages called reduction and regeneration. And I'll talk about, I have the next 3 slides, I'll talk about each of these stages in a little bit more detail, kind of show you what's happening and what's produced. Okay, so there's a lot of text on here. Mostly because, like with the those light reactions and at the beginning of photosynthesis, I wanted to make sure you guys could come back to this and kind of read through it rather than just having a diagram. So because this is a sort of confusing, I wanted to make sure it was explained well on the slides if you guys are going back to them, which hopefully you are. Okay, so in order to make glucose, like I said, we need carbon. Plants use carbon dioxide to do that. So that's why plants take carbon dioxide out of the atmosphere, which we love, right? So it's good for the atmosphere to take carbon dioxide out. That's going to go to make the glucose. So here we have, we'll start up here on the cycle. These little purple dots are carbons. So we're just looking at the carbons again in these molecules. So we have 3 CO2 molecules. Each one of those only has 1 carbon, right? So we just have 1 little purple dot. So for each cycle that happens, you need 3 molecules of CO2 to come in. So all 3 will come in to start the, I guess, keep the cycle going. Those will attach to or bind to this thing called RUBP. You don't need to know the actual name, but I put it here, ribulose bisphosphate. If you just know RUBP, that's fine. So CO2 plus RUBP, 3 of each, right? So 3 molecules of each of those are going to bind together and produce a 6 carbon molecule. Okay. That is done through a really important enzyme. We haven't really talked about any other enzymes. This is the only enzyme that I want you to know the name of, and it's called rubisco. It is the most abundant enzyme on Earth because plants need a lot of this to make this process happen. And there's a lot of plants on Earth. A huge volume of photosynthesis is happening. So you have rubisco basically gluing these 2 together. That's how you can think of it. So 3 carbon dioxides, 3 RUBPs. And you get something that you don't need to know the name of. So just know these pieces have to come together to kind of start the cycle. CO2 plus RUBP binded together using rubisco. That's the carbon fixation step.
Rubisco is the one that actually brings them.
It's an enzyme that allows this reaction to happen. Yep.
I have a question.
Yes.
Okay, that enzyme, is that the only enzyme for like photosynthesis altogether, or just the first step of carbon fixation?
Yeah, that's the only one you need to know. There's other enzymes at play that are kind of breaking stuff down and putting it together, but that's the only one you need to be familiar with.
Okay.
Similar to respiration, I said there's enzymes making all of this happen, right? But You guys don't need to know the names of all of the enzymes. Just know that enzymes are critical for essentially most of these steps. Rubisco, I point out in particular, just because it's the most abundant enzyme on Earth, and it's a really important part of photosynthesis. Okay, so I already said we need 3 CO2s for 1 cycle. So now we're going to move. So here's carbon fixation. Our next step is reduction, which is where we're going to make ATP and use those, or sorry, break down ATP and break down our electron shuttle. So that'll be on the next slide, but that's what's coming up. Okay. So in the reduction phase, we're using 6 ATP. So this is per cycle. 6 ATP, 6 NADPH. So basically, when I say we're using NADPH, we're stripping that H off, which means we're taking off the electrons. And those will be used to produce this molecule down here, G3P. So I kind of brushed over G3P in respiration. In hindsight, maybe I should have mentioned it a little bit more. But G3P, don't worry about the name of it. It will go on to make glucose. So it's a 3-carbon molecule. That's why it has the 3 in it, G3P. So 6 of those are going to be made in 1 cycle. That's why we need 6 ATP. We need 1 ATP to make 1 of those molecules, right?
Okay,
So
GP3 makes the glucose. Okay, is it made in the cycle or is it just
later on. Yeah, so here I have G3P at the bottom. It's leaving the cycle to go make glucose.
Okay,
elsewhere.
like this, anything like GTP or is it already made?
It's basically this kind of intermediate molecule is changed around.
Okay.
The ATP and the NADPH are going to help with that. So they'll kind of rearrange it into G3P. Yeah, good question.
I have one more question.
Sure.
Okay, so if it makes 6 3-carbon molecules, but we need 3 for each cycle, how does it make 3? How does it make multiple when you need 3 for 1 cycle?
Okay, so you have,
If that makes sense.
kind of. I mean, I see the numbers in the Calvin cycle get really confusing. So yes, I understand kind of where you're coming from. And I'll see if I can answer that for you. So you have 3 CO2s coming in, which means you're going to make, if you just look at this, we don't care about the name of it. We have 3 of these 6-carbon molecules. So then if you kind of ignore all of this, but you chop that in half, then you have 2 of the, so we have 3 of these, sorry. So there's 3 of these 6-carbon molecules, right? You chop those in half, then you have 6 3-carbon molecules. So then that's where you get the 6 G3P being made.
Oh, so the 6 is just the splitting of the
Yeah.
yeah.
So this long molecule up here, so this 6-carbon molecule that is kind of the beginning of the Calvin cycle, you have 3 of those. So if you cut those in half, then you have 6. You have 6 molecules that are only 3 carbons each.
Okay.
So down here, you get 1 of those 3 carbon molecules leaving, and the other 5 are going to stay in the cycle.
So you only need 1 G3P to
You
leave.
Good question.
For
You need 2. You'll need 2 to make 1 glucose molecule. So I have that here.
Why is there 5 leaving?
Because
why is it 5 leaving if you
that's a good question, and that
need 2?
So, yeah, so I'll get to, basically photosynthesis is really inefficient. It's like super inefficient. So you need 5 of these just to go back to make these 3 RUBPs. So you're going to have 5 of these to make this final product. That's why it's called the regeneration step, which I'll get into next. So to regenerate these 3 RUBPs at the end, you need 5 of these. So that means only one can go to make glucose with each cycle. So you need 2 cycles of the Calvin cycle to make. Yep.
So you need two.
You need 2 cycles to make 1 molecule of glucose, which I put here. So you're going to need 2 of these G3Ps because there's only 3 carbons. We know glucose has 6 carbons, so we need 2 of these. So not only do you need 3 carbon dioxides coming in for each cycle, you also need the cycle to happen twice just to make 1 molecule of glucose.
Okay, so after that one leave and you have 5 and it goes to the regeneration, is it gonna add 1?
Is it
gonna add back to get 6 to restart?
No, just not.
Oh yeah, so it'll basically rearrange. So that's why we're using some more ATP here, so that those 5 G3Ps will rearrange back into 3 RUBPs, and then we'll start all over. So we'll go back to having 6 of these 3 carbon molecules.
So it's like you're starting all over.
Yeah. Does that make sense?
Okay.
Yeah, more or less. Okay. So yeah, we're making 1 of these G3Ps. You put 2 of those together essentially, and you get a glucose molecule. So we're not even going to talk about that whole process. We're just going to imagine, yep, that will, once 2 of those come out of the cycle, you get 2 G3Ps coming off of this Calvin cycle, then you'll get a glucose molecule. Okay.
What are the ATP and the NADPH? What are they doing?
These, so they're powering kind of the rearrangement of PG, of this intermediate, into G3P. Yeah, so the ATP and the NADPH are donating electrons as well as providing energy.
Okay, because I was about to say, is it losing an electron right there because they had an H and then a lost?
Yep,
H?
exactly. So each of these NADPHs loses an electron. All of this is basically powering the rearrangement of this intermediate molecule called PGA to make G3P.
Okay. So it's like going like this.
Exactly. It's mixing it all up to make it the right molecule eventually. And that's why enzymes are important too. Enzymes are helping with all of that. But yeah, there's a lot going on here, obviously, that I'm not going into. So, but those are all good questions. It can get confusing when I simplify it too much, I realize. So yeah, if you're ever confused about any of the in-betweens, I can try to kind of smooth it out for you. So hopefully that makes sense up until, so this is just the reduction step over here, where we're going to make that G3P. One of those, like I said, is leaving the cycle off to make glucose. The other 5 stay in here to keep the cycle going. Okay, so yeah, the regeneration step is just regeneration of RUBP. So
this is the one we already talked about when it's like.
Mhm. Yeah, exactly. So we're regenerating RUBP. We need 5 of those molecules we made. That's why this photosynthesis is pretty inefficient in a lot of ways. Ideally, you wouldn't need to make 5 molecules just to keep the whole cycle going, right? But we do. That's okay. This is just how it works. So we rearrange these 5 3-carbon molecules using energy. And then you're going to get 3 RUBP from that. And the rearrangement process is somewhat complicated, so I'm not going to get into that. So yeah, so we're using 3 ATP. And then we have our 3 RUBPs that we need to bind with the 3 CO2 coming in. That'll bind together using Rubisco, and you start the process all over again. All right, so I think I have on the next slide just numbers of what's used. And then what is that, the input and the output, basically.
Like, before you go on,
Uh-huh.
can you like try to, you know how you just did the, you know how you did the like dependency and you said this is step you need to know, so this one, can you tell us like the major steps you need to know? So I feel like I got lost.
Yeah, you mean for all of the Calvin
Yeah.
cycle? Yeah, so, let's go, I mean, you'll need to know all, the bullet points that I have on here, I'm gonna go back to the first stage here. So the bullet points that I put up here are what you need to know. What I just went over with the light dependent reactions, that was kind of a zoomed out look. There are additional details that you need from the PowerPoint from that lecture that I didn't go over. But okay, if we step back, what are we doing? We're taking in CO2. Plants take in carbon dioxide, right? It is basically going to go to make glucose. Some of the carbon is going to go to make glucose. Some of the carbon just continues around the cycle. I think that's probably the very most basic take-home message. Yeah. We're using ATP and NADPH and all that stuff, and I'll give you the numbers in like a kind of a table format, more or less, in just a minute. But what we're doing, taking in that carbon dioxide, it's going to make glucose, the carbon in particular, through rearrangements and all kinds of stuff. Yeah. So does that help a little bit? Okay. Because yeah, it's easy. It's really easy to get lost in the details. And hard to see sometimes the forest for the trees. Okay. So that's the whole Calvin cycle. I think it's a little bit more confusing than the Krebs cycle, the citric acid cycle, just because the numbers are really weird. So you'll probably need to spend some time really looking at the Calvin cycle. The bullet points, like I said, that I put on each slide are what you really want to know. Hopefully the diagram helps explain it a little bit, if you're a little bit more visual. Okay. So going on to the inputs and outputs of the Calvin cycle. So what I'm going to do here, so this is a weird cycle, right? Because you have one cycle, but you need two cycles to actually make a glucose molecule. So I've got the inputs and outputs for one cycle, and then we're just going to obviously double all of those to make one glucose molecule. Okay. So used in one cycle, we're using 3 CO2. That's what's coming in at the very top of that cycle. We need 9 ATP and 6 NADPH. So if you look at the cycle, you should be able to add all of those up based on the numbers on that previous slide. And then what do we get from one cycle? The G3P that we make from one cycle is going to go on to make the glucose. And then these other two are just basically the opposites or the complementary pieces to the ATP and NADPH, right? So if you're using ATP, you're creating ADP. So those numbers are the same. If you're using NADPH, you're going to chop off that H, that electron, and you have NADP plus.
Because we lose our electrons in the cycle.
Yes.
Okay.
Yeah, to rearrange one of those molecules. Yeah.
And how do we still end up with 9 ATP? Oh, it changed.
Yeah.
ATP.
Yeah, ATP to ADP. That's easy to overlook. The really important output of this is the G3P, right? Because that's what's going to make the glucose. So we have one G3P from one cycle. Okay, so then let's look at, so we need 2 rounds of the Calvin cycle to make one glucose molecule, because we need 2 of these. 2 G3Ps. So the input total, obviously, I'm just doubling what is up here. So this is just double. 6 CO2, 18 ATP, and 12 NADPH. That's what's going into it, into one glucose molecule, into making one of those 6 carbon glucose molecules. here you get our 1 glucose. Yay, 2 of those G3Ps. That's our goal. Okay, any questions about these numbers at all? So we doubled the ATPs, we doubled the NADPHs, we doubled the CO2s.
So I'm sorry,
Mhm.
G3P is really just CO2, that's, what's the actual, like, element?
Oh, it's a 3 carbon molecule, so it's kind of complicated, but yeah,
Okay, I have a question.
sure.
Okay, so how many ATPs, like, you know, in the circle, like I've seen like ATP and ADP like on the first round,
Mhm.
and then on the generation side.
Right.
Like, but how are you getting 9?
So let's go back. So, well,
Oh, okay, 6 on the first for the carbon fixation, and then 3. Okay, I got that. I got it. I was confused a little bit.
yeah. So some of them are made over here, or some is used here, and some is used here. Yeah.
Okay.
So 9 total. All right. Any other questions about these numbers? Okay, that wraps up, I think, the worst parts of photosynthesis. Like I said, thank you guys for hanging in there. This is not the funnest unit to learn or to teach, but we're almost through it. If you find it interesting, awesome, good for you. Biochemistry is not my favorite, but that's okay. It's important because it's what makes us all live, right? Okay. So let's talk like big picture. Let's let's move away from chemistry and talk about why photosynthesis isn't actually all that efficient. And there's actually a few different kinds of photosynthesis, so different ways that plants actually make their glucose. So normal photosynthesis is called C3 photosynthesis because it makes that G3P. I assume that's why they call it C3. It's very inefficient, especially when it's really hot and dry. Oh, no, is this the old one?
Are you talking about the fish of the cactus?
Yeah, hang on, guys. I forgot to put the updated version on the jump drive here. Give me a few minutes.
So when you mean normal, you mean like just taking in the sunlight and you don't do that?
Yep, and the plants will still do that. There's just a slight change in not how they take in the sunlight, but how they take in the CO2 essentially. So hang on, everybody. Okay, back to it. Yeah, so it wasn't just the picture of the desert that I was missing. The rest of the slides were, they had too much detail on them. So this is a simplified version. This is what is on Canvas. Are you guys looking at Canvas? Okay, I was like, I'll double check and make sure this is what's on Canvas. Okay, so back to this. So yeah, normal C3, very inefficient, particularly in really hot and dry climates. So think desert. Or a lot of like the plains of the US can be really hot and dry. So what happens when it's really hot and dry, plants don't want to lose water, right? So they need water for this whole process to happen. So in hot and dry conditions, those stomata, if you remember me mentioning them a while ago, they're little pores in the leaf. They let gases in, but they also they lead to water loss in a plant. So water will come out of those stomata. The stomata need to open to be able to take in CO2 for the Calvin cycle.
Okay, so like tomatoes are like pores?
Mhm, pores on the leaf, yeah. So the stomata in really hot, dry conditions, think the desert, are going to close if it's too hot, because otherwise too much water will be lost. So that means there's no CO2 coming in, which makes it difficult for the Calvin cycle to actually work, right? If there's not enough CO2 coming in to start that whole process. So oxygen builds up, and rubisco, that really important, the only enzyme I've really asked you to know, binds to O2 instead of CO2. So at the very beginning of the Calvin cycle, up there at the top, where CO2 and rubisco are supposed to bind, it binds with oxygen instead. So it shuts down the whole Calvin cycle. And it can lead to, like I said here, up to a 50% loss of carbon in a plant. So much, much less glucose is made if the stomata are not open, and if CO2 or if O2 is binding to rubisco instead of CO2.
Okay, I have a question.
Mhm.
What is the what does the stomata does? Like, what is the importance of it?
What's the purpose of it?
Mm-hmm.
The stomata are like little pores. So they open up and they let CO2 in. So here, I'll show you on here. Carbon dioxide goes into the leaf that way. That's the only way carbon dioxide can get into the leaf. And inside the leaf is where the Calvin cycle happens.
Okay, so it's all about the leaves with photosynthesis.
Yes, exactly. So the leaves are taking up the carbon dioxide, but they have to take them up through these pores that they can open and close.
Okay.
Like it shows here in this diagram, water also gets lost, not really on purpose, but it's going to evaporate out of the pores if it's really hot and those pores are open. So that's also not good. Does that make sense?
It does.
Okay. So those are the problems, and the solutions are that there's a couple different pathways to kind of combat this issue with not being able to open the stomata as much. Again, this is in hot, dry conditions. In the Southeast, it gets hot, but it's not dry. So we don't really have this issue down here. So the goal is really to decrease water loss. And like I said, they're common in hot and dry regions. So the names are the C4 pathway, so instead of C3, and then the CAM pathway. And I'll tell you what each of those are in just a minute. Just very basically, just to let you know, there's different ways that photosynthesis can happen. And we're not going to get into any of the like cycling or biochemistry, just some slight differences sort of at the beginning of the Calvin cycle. All right, so first, the C4 pathway basically uses carbon dioxide more efficiently. So C4, instead of using rubisco, which loves to bind to oxygen instead of carbon dioxide, which is not good, it uses a different enzyme. You don't need to know the name of it, but it uses a totally different enzyme that will basically not bind to oxygen.
Okay, so does this not go through the cycle?
It does. It goes through the cycle still, but it doesn't use rubisco. So where that rubisco was on the cycle, it's another enzyme.
Okay, but we don't need to know that. We just need to know.
Yeah, just know it uses a different enzyme. Yeah, this is kind of very just basic information. We don't need to get into like a lot of the details. Oh, there we go. Of exactly how this works. But yeah, different enzyme means more efficient use of carbon dioxide. So if there's not a lot of carbon dioxide in the leaf because the stomata haven't been open and haven't let in carbon dioxide, it's not really as much of an issue because this other enzyme still binds to that little bit of carbon dioxide that's there. It won't bind to the oxygen instead. So a lot of grasses use C4 photosynthesis, and you might be thinking, who cares about grasses? But most of our main crop plants, like stuff that we eat, are actually grasses. So you may not know that, but they're in the grass family. So corn, sugarcane, wheat, sorghum, all of those are grasses. So this means essentially that we can grow these really important crop plants in a lot more areas than we could grow, say, a C3 plant. So these C4 plants can grow over more area in the globe, which is good for us as people. Okay, so that's C4. I think I have just enough time to finish up the CAM photosynthesis. Any questions about this? Different enzyme, take-home message, it's just more efficient. CAM photosynthesis, the term comes from crassulacean acid metabolism. Crassulaceae is just the family that most of these plants are in. So cacti are in that family. You don't have to know crassulacean acid metabolism. I just put it up there in case you were interested, but you can just know CAM photosynthesis. The goal here is really to minimize water loss. So C4 plants, a lot of grasses. CAM plants, like I said, are usually in the cactus. They're a type of succulent plant. So succulents are those that basically suck up a lot of water, like a cactus, and hold on to it. So they grow in extremely dry areas. So here we're talking about mostly desert plants. So the goal is really to minimize water loss. And water loss in the desert, when does evaporation usually happen in the desert, day or night? Like when does more evaporation happen? During the day, yeah, it's hot, it's sunny. So there's a lot of evaporation of water during the day. So the plants want to close their stomata during the day. That way they don't lose any water or as much water. And they open them at night. So they'll open the stomata at night. They don't lose nearly as much water that way, and they get enough CO2 in there.
Does this one still use this one?
Yes, this one uses, well, good question. I say yes. I can't remember. I can't remember if it uses the other one.
And
I'll find out.
allows it to open this. Do we need to know that?
You don't need to know it, but I mean, it's just, I don't know how plants like think about what to do, but it's just their, so these are different photosynthesis pathways that have evolved over time. So it's just what they do. Yeah. Without getting into too much detail. Yep, so open at night, close during the day. That's actually pretty straightforward. They lose less water that way. I think they might use the other enzyme. I can't remember now. I have it on the old slides. Okay, that wraps up photosynthesis. And on Friday, we'll do review. I'll have a Kahoot quiz. I'll get that posted hopefully later today, maybe tomorrow. We'll do that on Friday. And then I might run through a few things on the board just to remind you of some of the main pieces. It does use a little bit on here. I was like, I don't have it on here.